Let's talk about how to use the law of sines to solve a non-right triangle when two sides and the non-included angle are given, which is also called the ambiguous case. As a reminder from our previous video, the law of sines is this proportion, which is just a side length over the sine of the angle that's opposite from that side. So A over A, B over B, C over C. And we learned in the previous video that the law of sines can only be used in an angle-angle-side, angle-side-angle, or side-side-angle situation. We've already seen examples in the previous video of how to solve if it's angle-angle-side or angle-side-angle because it's pretty straightforward. But in this video we're going to focus on the side-side-angle case, which is also called the ambiguous case because there might be one answer, two answers, or no answers that satisfy the given measurements. The Merriam-Webster dictionary defines the word ambiguous as capable of being understood in two or more possible senses or ways. And in our world of geometry, the word ambiguous means that there might be different numbers of solutions. There could be one, or none, or lots. But for what we're doing today with the ambiguous case, our options are one triangle, no triangle, or two triangles that satisfy the given information. Part of the process of solving an ambiguous case is calculating the height of the triangle, and typically that's not a measurement that's been provided to you. Instead, we're given one angle measurement and two side lengths, so we need to use the information that we've been given and combine it with some trigonometry from earlier in this unit to come up with a way to solve for the height. The height is really just an altitude, so if I drop a perpendicular line from angle C down to side C, I could call that h for the height. When I do that, it makes a right triangle. And I could calculate h using trigonometry, because h is opposite from the angle that we know, and b, which is one of the side lengths that we were given, is the hypotenuse of this little right triangle. And we know that the sine of an angle is equal to opposite over hypotenuse. So I could state that the sine of angle A is equal to h over b, which is opposite over hypotenuse. But we want to solve for h because we're interested in knowing what the height is each time, so we'd really rather have this as h equals instead of sine of a equals. So to solve for h, I'll just multiply both sides by b, and that's where I get this formula from. H equals b times the sine of a. Another piece of information that we're going to need to know in order to solve these problems is the fact that the sine of an angle is equal to the sine of its supplement. For example, if you were to type in the sine of 32 and the sine of 148 into your calculator, both of those are going to give you the same answer of 0.5299 ... And that's because those two angles are supplementary. 32 plus 148 equals 180 degrees. The explanation for why this works the way that it does is a little bit beyond what we need to be focusing on in this class, so just take my word for it basically, and you'll learn why this is the way that it is in a future course. So how do we determine the number of triangles that we're going to get for our answer? In general, there will be 0 triangles, there will be no solution, if the sine of angle B is greater than 1. Whereas there will only be one valid triangle if the supplement of angle B is too large to fit into the triangle. Remember that we just discussed how the sine of an angle is equal to the sine of its supplement as well. And basically what this is saying is that if you find the supplement of what is supposed to be the answer, and that number is too big to make a triangle, that it would be more than 180 degrees, then you know that the first version of the angle was really the only one that worked. And finally, there will be 2 valid triangles if the supplement of B is small enough to fit into the triangle. It's possible to get one answer, but also find the supplement of that answer, and that would fit into the triangle as well, in which case you would end up with 2 valid triangles. And that all basically gets broken down in this chart. And I'm going to be explaining why this chart is the way that it is in all of the examples that we're about to look at together. But in a nutshell, what you're doing each time is comparing the length of A, which is the side that's across from the given angle, and the length of B, which is the side that's adjacent to the given angle, and the length of H, which is the height of the triangle, which remember we just discussed a few slides ago. You can calculate the height of a triangle using B times sine of A. So let's look at a few completed examples so we can analyze why they ended up with no solution, one solution, or two solutions. Let's say we were given these 3 measurements. We were given the measure of angle A is 62 degrees, The length of CB, which we could also call little a because it's across from angle A, is 34 units, and the length of little b is 40 units. Since this is a side-side angle situation, we could use the law of sines to solve. To set up the law of sines, you put the side length over its opposite angle's sine, so I did 34 over sine of 62, and then do that again for 40 over the sine of b. Then I would cross multiply and solve, and I end up with sine of b equals 1.0387 ... But if you do the inverse sine of that number to get b alone, it's going to tell you a domain error. It's not possible for the sine of an angle to be bigger than 1. So what's actually happening here? Why did we end up with a number that's not going to work? It's because that triangle that you were given doesn't actually exist. The length of A that we were given is too short to actually reach all the way to the other side. There's a tiny little gap here, because there's no possible way to make these three measurements into a triangle. So then how would it be possible to have two different solutions? This time we have the measure of angle A is 62 degrees, the length of little a, which is across from angle A, is 37 units, and the length of little b is 40 units. So I'll set up my law of sines, 37 over sine of 62, because that's the side length and the angle across from that side length, equals 40 over sine of b, so side length over angle across from that side length. So I'll cross multiply and solve, and this time the sine of b is a number that's less than 1. So when I type that into the calculator, when I take the inverse sine of both sides, I find out that the measure of angle b is 72.6571 yada yada degrees. So now that I know the measure of angle A is 62, the measure of angle B is 72.7, I can figure out that the measure of angle C is 45.3 degrees. So it looks good, done, right? But here's the problem. The supplement of angle B would be 107 degrees. These two numbers add up to 180. And if I put this 107.3 number in for angle B instead of the 72.7, add up these three angles to 180, I get 10.7. So this is another valid triangle. A triangle with these two side lengths and these three angle measures would also exist. So what's happening here? It's because this side length of A, 37 units, could be in this orientation, where it makes a 45.3 degree angle at angle C, or it could also swing inward and create this triangle over here, in which case angle C is only 10.7 degrees. But both of these triangles have an angle measurement of 62 degrees for angle A, and side lengths of 40 and 37 for B and A. It's just that A is this specific side length between being too short and too long that it can swing in two different directions to create two different triangles with this information. So then how do we ever only end up with one solution? Well, in this example, we have angle A is 62 degrees again, little b is 40 units again, but this time little a is 42 units. So set up my law of sines, cross multiply, the sine of b is less than 1, so I can calculate its measure, use the inverse sine of both sides to find out that the measure of angle b is about 57.2 degrees. So if I plug that in to my triangle sum formula, 62 plus 57.2 plus the measure of angle c, and I get that the measure of angle C must be 60.8 degrees. So it looks good, but is there more? Is it like last time that if I find the supplement, it would also work? This time, no. The supplement of angle B in this case would be 122.8 degrees. So if I do 62 plus 122.8 plus the measure of angle C, the measure of angle C ends up being negative 4.8 degrees. And that's not possible. You can't have a negative angle measure. So in this case, the only angle measurement that would create a valid triangle is the original, 57.2 degrees. I like to call this the Goldilocks triangle because it's the one that's just right. You get one answer, not no answer, and you only get one answer, not two answers. A is just long enough to reach the third side, but not so long that it's able to swing inward and create a second triangle. So let's give a few examples a try. This is a side-side angle situation, so I do need to use the law of sines to solve, But before I do, I need to determine how many solutions am I looking for. Before you get started, go ahead and label your sides that you've been given with lowercase letters because it'll make filling in the height of a triangle formula a little bit easier. So 82 I'm going to label with a little a because it's across from big A, and I'm going to label 43 with little b because it's across from big B. And you could also label the third side as little c, but you don't really need it. The formula for the height of a triangle is b times sine of a. So h would be b, which is 43, times the sine of angle A, which is 77. So type that into your calculator and we get about 41.9 meters. What we need to do now is compare the lengths of A and B and C. A is 82, B is 43, and H is 41.9. So now we need to put them in order from biggest to smallest. And they actually already are. A and B and H are already in order from biggest to smallest, so I can write that A is greater than B is greater than H. So we're going to use that chart to figure out what exactly that means. Part of the chart asks you whether A is acute or obtuse, and in this case A is acute. So we're looking in this part of the chart, and I see A is bigger than B, which is bigger than H right here. It says that there must be just one triangle. So let's see if that's true by solving. I'll set up my law of sines proportion. I'll put the side length that I know over the sine of the angle that I know, so 82 over sine of 77. And I'll set that equal to the side length that I know over the angle that I don't know, so 43 over sine of b. Cross multiply. I get 82 times sine of b equals 43 times sine of 77. Divide both sides by 82, and the sine of b is less than 1, so I know I at least have one answer. Take the inverse sine of both sides, and I find out that the measure of angle b is 30.7 degrees. So using the triangle sum theorem to figure out the measure of the third angle, 77 plus 30.7 plus the measure of angle c equals 180, and I find that the measure of angle c must be 72.3 degrees. Our chart told us that we're looking for only one triangle, but why is that? Well, the supplement of 30.7 would be 149.3, right? That's what you would add to 30.7 to get to 180. So if instead of writing 77 plus 30.7 plus the measure of angle c equals 180, we substituted the supplement of 30.7. In other words, you said 77 plus 149.3 plus measure of angle c equals 180. You would find out that the measure of angle c is negative 46.3 degrees, and that's obviously not possible. So that's why we're only getting one solution from this problem, because the supplement of angle b is too big to fit into this triangle. So I now know all three of my angle measurements, but I'm still missing one of my side lengths. So let's use the law of sines to figure that out. I'll write the same ratio to get started as I did on the first part of this problem, 82 over sine of 77. But this time I'll set it equal to the length of AB over the sine of 72.3. And again, it has that dot, dot, dot. We talked in the previous video that you should round your answers, but you should not round those numbers when you're doing it with your work. So don't just multiply 82 times the sine of 72.3. Multiply 82 times the sine of that entire answer that you would have gotten from all of the decimals you've had along the way in your work. So cross multiply, solve using the full decimal, and we find out that AB must be 80.2 meters long. Let's try another one. We have another side-side angle situation, which means we need to use the law of sines to solve, but first we need to know how many solutions there's going to be. Label the side across from angle A as lowercase a, and the side across from angle B as lowercase b, and if you want to, go ahead and label the third side with little c. However, this time, we don't really need to calculate the height because angle A is obtuse. All we need to do if angle A is obtuse is compare the length of A and B. A is 35 and B is 27, which means A is longer than B. So if we look at our chart, if A is bigger than B, then there is exactly one triangle that satisfies those measurements. So let's see what it is. The first ratio that I'll set up is the side length that I know over the sine of the angle measure that I know, so 35 over sine of 106. And then I'll set that equal to the other side length that I know over the sine of the angle that I don't know, so 27 over sine of b. Cross multiply and solve. The value for the sine of b is less than 1, so it looks like we do have a triangle to solve for. The measure of angle b is 47.9 degrees. So now I can use the triangle sum theorem to figure out the measure of angle c. 106 plus 47.9 plus the measure of angle c equals 180, so angle c must be 26.1 degrees. So why aren't we getting two different triangles from this? Well, because the supplement of 47.9 degrees is 132.1 degrees. So if I write the supplement of 47.9 degrees here instead of 47.9 degrees, in other words, if I do 106 plus 132.1 plus measure of angle c equals 180, we would find out that the measure of angle c would have to equal negative 58.1 degrees, and that's just not possible. So there must be only one triangle that satisfies these measurements, and it has angle measures of 47.9 degrees, 26.1 degrees, and 106 degrees. So I know all three of my angle measurements now, and I know two of my three side lengths, but I still have one side length left to solve for. So I'll start out with the same ratio as I did before, 35 over sine of 106, but this time I'll set it equal to the length of AB over the sine of 26.1. Again, keeping all of the decimal points with this number, don't just round to 26.1 for your work. Cross multiply and solve, and I find out that AB is about 16.0 feet long. So let's figure out how many solutions our next problem is going to have. Label the side opposite angle A as little a, the side opposite of angle B as little b, and you can label the other side as C. And we're going to calculate the height of this triangle. We need to do that this time because angle A is acute again. So if you have an acute angle for A, you need to calculate the height so you can compare the height to A and B. If it's obtuse, like on the last problem, all you need to do is compare A and B. The height is equal to little b, which is 26, times the sine of big A, which is 43. And your calculator will tell you that that means h is 17.7. So now we need to compare A, B, and C. A is 19, B is 26, and H is 17.7. So rearrange these numbers to be in order from biggest to smallest. That would be B, and then A, and then H. So B is greater than A, which is greater than H. So looking at our chart, I see that right here. BAH would be two possible triangles. So we have two different answers that we're going to get when we solve this triangle. Start out with the law of sines, 19 over the sine of 43. That's the angle that I know and the side that I know, and set that equal to 26 over the sine of B. That's the other side that I know and the angle that I don't know. Cross multiply and solve. Sine of B is less than 1, so I know I'm going to have an answer. The measure of angle B ends up being 68.9 degrees. So using the triangle sum theorem to calculate the measure of angle C, we find out that it's 68.1 degrees. And we could use that information to solve for the third side length, 19 over sine of 43 again, and this time I'll set it equal to AB over the sine of 68.1. Cross multiply and solve, and AB is 25.8 centimeters. So that's the answers for the first version of this triangle, but the issue is that the supplement of angle B is small enough to fit into this triangle to create a second triangle. Let's take a look. In our first triangle, we found that the measure of angle B was 68.9 degrees, but the supplement of 68.9 is 111.1. So if I plug that into the triangle sum formula, putting 111.1 in place of angle B instead of the 68.9 that we used originally, we get a valid angle measure. That would be that the measure of angle C is 25.9 degrees. So now I can use that measurement to figure out a different length for AB. So I'll use that same 19 over the sine of 43 ratio, but this time I'll set it equal to AB over the sine of 111.1 degrees instead of 68.9 degrees. So cross multiply and solve, and this time we find out that AB would have to be 25.99, or you could go ahead and round that up to 26 centimeters. And let's take a look at one more example. Label 44 as little a and 72 as little b, and then calculate the height of this triangle using b times sine of a. So h would be 72 times sine of 39, so h would be 45.3 inches. So A is 44, B is 72, and H is 45.3. Rearrange those numbers so that they're in order from biggest to smallest, and I get that B is greater than H is greater than A. But when I look at the chart, that's not one of my options. I don't see B is greater than H is greater than A anywhere. So instead what we're looking at is actually this first one, that A is less than H. The length of one of my sides was less than the length of the height. That's not possible. There is no triangle for which that would be true. Basically what we're saying is this triangle is a lie. There is no way for this 44-inch side to actually be long enough to reach all the way over to side AB. So your answer just is no triangle. And that's all you need to know about solving the ambiguous case for a side-side angle situation. In our next video, we're going to learn how we can use trigonometry to calculate the area of a triangle.